AP Chemistry, this is the review assignment for the test that will be held on Friday, December 1st. So these are the topics that will be on the test. Lewis dot structures, formal charge, resonance structures, net ionic equations, activity series, and solubility rules. Okay, so let's get going on this. So draw a Lewis dot structure for this. So your best guess as to what the shape is just probably the same as the chemical formula, with the least electronegative element in the middle. Now we have to count the valence electrons. 1 hydrogen times 1 valence electron. Okay, so you have a total of 10 valence electrons among those 3 atoms. So the first thing you do is you create single bonds between the central atom and the terminal atoms. That uses 4 of the electrons. Now you create octets around the terminal atoms. Well, hydrogen already is full. 2 electrons is all that it can hold. So we'll go over to nitrogen. Okay, so now nitrogen has an octet. And we've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've used all 10 electrons. But carbon doesn't have an octet. So that means we don't want to add or subtract any electrons. We just want to move some. So we're going to take this lone pair on the nitrogen. We don't want to take the octet away from nitrogen, so we want to put it somewhere where it stays with nitrogen. So we're going to put it right there. Same with this one. We're going to put this one right here. So it's a triple bond. That's what that's indicating. So nitrogen has an octet, carbon has an octet, 6 plus 2 is 8, and hydrogen already had an octet. So that's how you would do that. Okay, now we're going to do a formal charge to determine which of these configurations of CO2 is the most desirable one. So the formula for formal charge, what you're saying with formal charge is oxygen naturally has 6 valence electrons. When it's in this chemical bond, it would like to continue to feel like it has 6 valence electrons because that's what makes it happy. That's its comfort zone. So what we're going to do is see if it feels like that. So we're going to start with the number of valence electrons for each atom. And then we're going to subtract the number of lone pair electrons, not the number of lone pairs, the number of lone pair electrons. Total number of electrons. And then we're going to subtract half of the bonding electrons. So here there are 4 bonding electrons between oxygen and carbon. So the way you do this, you just assume that carbon owns 2 of them and oxygen owns 2 of them. So oxygen owns half of the bonding electrons. So it's minus 1/2 bonding electrons. Okay. So let's go ahead and plug in the number. So oxygen has 6. You get this off the periodic table. If you don't know how to figure this out, you got to come talk to me. Oxygen has 6 valence electrons. Let's label this oxygen on the left. Minus the number of lone pair electrons, 1, 2, 3, 4. So it's minus 4. Minus half of the bonding electrons with carbon here. 1, 2, 3, 4. So half of 4. So 6 minus 4 minus half of 4 is 2 equals 0. So what that means is oxygen naturally has 6 valence electrons. And in this chemical bond, it feels like it has 6 electrons, so it's happy, it's comfortable. You want that number to be 0. All right, now we're going to do the carbon. Carbon has 4 valence electrons naturally. It has no lone pairs in this chemical bond. And it has 1, 2, 3, 4, 5, 6, 7, 8 bonding electrons, so half of 8. So 4 minus 0 minus 4 is 0, so carbon is happy. It feels the natural number of valence electrons. Okay, now the oxygen on the right. Again, it has 6 valence electrons in its natural state. 1, 2, 3, 4 lone pair electrons, minus half of these bonding electrons over on this side. And that gives us 0. So everybody's really happy. Everybody's got 0. Means they're feeling the same amount of charge around them that they would feel if they weren't bonded, if they were just natural atoms. Now let's look at this one. This also meets the rules. Everybody has an octet and you've used the correct number of electrons. So let's check this one out. So O on the right. Let's do left. Sorry, let's do it the same way we did the last one. Okay, so again, oxygen has 6 valence electrons. That's when it's not bonded. So that number doesn't change. Now here it has 1, 2, 3, 4, 5, 6 lone pair. And then it has 1, 2 bonding electrons. So half of the 2 bonding electrons. And 6 minus 6 is 0, and half of 2 is 1, so minus 1. Going to give you -1. Okay, so that's not quite happy. It's got an extra charge on it, negative charge that normally oxygen would not want. Okay, how about carbon? So 4 minus, it again has no lone pairs, and it has 8 bonding electrons total. So half of 8. So again, even though the bonds on carbon look lopsided, it's still okay with that. It's going to be a 0. Now we do the oxygen on the right. 6 minus 2 lone pair right there. Minus half of 1, 2, 3, 4, 5, 6. So 6 minus 2 is 4, and half of 6 is 3, so 4 minus 3 is +1. Okay, so you notice it is charge balanced, okay? This has no charge on it, and -1 plus 0 plus +1 is 0. However, this one has an extra charge that it really doesn't like to have, this one on the left, and this one is deficient a charge. It would like to have one more charge, one more electron that it doesn't feel. That's this one over here. So it's not quite as stable, not as happy. So this is the more stable configuration. The closer you get to 0, the more stable the configuration. All right, let's keep going. Now I'm going to ask you a series of questions on net ionic equations. The first one will simply be taking the names of compounds and turning them into chemical formulas. So here we have Pb, lead, and it's a lead 2. There's more than one charge that lead can have. That's why you have to put the Roman numeral. So it's a 2+. It's a cation. And then nitrate, that's NO3. Okay, and where do we find that? We come over to, okay, so we come over to the 60 common ions, and we come down to the third group, and we see nitrate has a 1- charge, NO3, and it's a 1- charge. So we're going to put a 1- there, plus lithium. Again, we come over here. Now you can go to your charge number by ion, or you should be able to tell this just by looking at the periodic table. Lithium is in the first column, so it's going to lose an electron to be like the nearest noble gas, which is going back to helium. Or you can just look at it right here on this common ionic states sheet, and that's the Li1+. So it is a 1+. And bromine, you come over here, there it is, second to last column, it's a halogen, it's a 1-. Okay, so lithium bromide is charge balanced, but lead nitrate is not. So you cross the arrows, and what you get here is Pb, parenthesis, NO3, and then a 2 outside, this 2. So this is a 1- charge, this whole thing right here. So it's 2 times 1- equals 1, 2+. So they balance out, 2 minus 2+. And these two are already in balance. You don't need any subscripts. So it looks like that. Okay, so that's the answer to this one. Okay, show the double replacement reaction for the following reactants. So all you're going to do is take the cations, the metals, the potassium and the calcium, and switch them. So you're going to end up with CaS plus, you're going to end up with K2 and I. You just switch these two. Now this is not balanced, okay? You do that in a later step when you're doing a net ionic equation. I just want to see you show the double replacement reaction where you switch the calcium and the potassium, okay? All right. So that's how you do that, okay? Now, charge balance the following reactants. right? The reason I'm not having you just do one long net ionic equation is because if you make a mistake early on, it's going to carry all the way through and you won't get later parts of the problem correct, okay? So charge balance. So sodium, come over here. Sodium is a 1 plus right there. Sulfur is a 2 minus right there. Again, you should be able to just look at your periodic table and tell that by where they're positioned. Calcium is a 2 plus right there. Fluorine is a 1 minus right there. Come on over here. Sodium is still a 1 plus, fluorine's a 1 minus, calcium's a 2 plus, and sulfur is a 2 minus. Okay, so if they're the same number, then you don't need to write subscripts. So this is NaF, 1 and 1. Now 2 and 2 reduces down to 1 and 1. Okay, it's two of these for 2 of these, but that means there's 1 calcium for 1 sulfur. You need one of the 2 pluses to balance with the 2 minus. So it's just CaS. Over on this side, you need to do the crossing arrows. So you have Na2, S. So S is a 2 minus. So you need 2 of the 1 pluses to balance with the 2 minus. Same thing with the calcium and the fluorine. You need 2 of the fluorines to balance with the 1 calcium. So it's CaF2. Okay, so that's charge balancing each of the compounds. It's not the entire equation, it's just each compound individually. For ionic compounds, each compound has to be electrically neutral. It has to be charge balanced. Okay, now we're going to have you write a complete ionic equation for this. This is straight off of one of your assignments. So what you do is this. You're going to break everything that's aqueous into ions. These 3. The solid does not get broken. It's a precipitate. It's going to stay bonded together in water. This does not dissolve in water. How do we know that? So now let's go look at that. I'll give you a couple of these problems in a minute about solubility. So K2SO4. K dissolves with anything right there. So it doesn't matter what it's with. It's going to dissolve. This is totally soluble. Next one, CaI2. Okay. I dissolves with anything except these 3, but calcium is not one of these 3. So calcium iodide will dissolve in water. So that's aqueous. That's what it means. It's going to dissolve if it's AQ. CaSO4, we come down here. SO4 dissolves with anything except for these 5 ions, and calcium is one of those 5, so that's an exception. That means that calcium sulfate does not dissolve in water. So it's going to stay bonded together, and so that's a solid. Okay, and finally, Ki. Well, again, K dissolves with anything, I dissolves with anything except these 3, so that's going to dissolve, so that's aqueous. So now you have to break these up, and when you write each of these, you have to write the state of matter, and you have to write the charge on it. Okay, so here we go. So what is this K2? Let's look at what it is. K2SO4, let's just make up a structure here. SO4 with a potassium and another potassium. I don't know what it looks like, but that's good enough. When it breaks up, it doesn't break up into a K2 molecule. There's no such thing. It breaks up into a K, another K, and the SO4. So it breaks into 3 particles. Okay, that. So the way you write that is 2K. That means you have 2 of the K's there. Now it's aqueous because it dissolved. And each K, not with the total of the 2 of them, but each K has a 1 plus. So you put that up here. Now you go to the SO4. SO4 has a 2 minus. So it's SO4. It dissolved, so it's aqueous. And it's a 2 minus. Where do you get that? You get that from your 60 common ions. Okay, and you would have already had it, but let's just show you. SO4 is sulfate, and it's right there. It's SO4 2 minus. It's a 2 minus charge. Oops, let me get up there, sorry. sulfate is SO4, 2 minus charge. Okay, so you're going to put that there. Now you just put another plus sign. So you break these up and you put plus signs between them. Ca is a 2 plus charge. And since it dissolved, it's aqueous. Again, you could get this on the charge number by ion sheet, or there it is right there. Ca is 2 plus. And you've got 2 iodines. So just like the potassium, it's not an I2 molecule. It's not a gas. It's in liquid. So it's 2I, 1 minus, and that's aqueous. Okay? So you broke up everything over here. Now we're going to come over here. Now this stays as a solid. You don't put charges on it. You don't put anything. You just put Ca, SO4, solid. Boom. That's it. Just write it exactly the way you see it there. And now this one is going to be 2Ks. So 2K, 1 plus, aqueous, plus 2I, 1 minus, aqueous. And that's the complete ionic equation. Okay, so I expect you to know that by name. When I say that, that's the long one. That's the big one. Now you write the net ionic equation. So you cancel out anything that appears on both sides of the arrow. I like to circle the arrow, be clear where that arrow is. So you have 2K on this side and 2K on this side, so they cancel. Those are called spectator ions because they dissolve into 2K at the beginning. They stay as 2K at the end, so they didn't do anything. They just sat there and watched the reaction take place. Spectator ions. Okay, here we have 2I right here and 2I over here. So that I is also a spectator ion. It doesn't do anything. Now we have SO4 here. We don't have SO4 by itself over here, so we'll circle that one. We have Ca over here. We don't have Ca over here. What we do is have those two combine to form Ca. That's a Ca, not a Cu. CaSO4. So that's the net ionic equation. So write it down here. I want to see you write this and this, okay? Do it properly. And that's the final net ionic equation for this. Okay, you don't write the charges on the solid, okay? All right, let's go on down here. Let's do some solubility problems. So go to your solubility rules, and all I want you to do is put an S or an I, whether it's soluble or insoluble. So the solubility rules are page 9 in your packet. There they are. Let me back this up a little here. Okay, so learn how to read this. Everything on the left side is soluble except for the exceptions, these and these. Everything on the right side is insoluble except for the exceptions. Now these are soluble with anything. Exceptions for all anions. Okay, so these are soluble with anything. Okay, so let's go. AgBr. Let's come over here. There's Br. And it's soluble with anything because it's in the soluble column except these three. And Ag is one of those. So that means AgBr is insoluble. PbNO3. Okay, so NO3 is soluble with anything, no exceptions. These up here are soluble with anything, no exceptions, okay? So PbNO3 is soluble. CaOH2. So OH is insoluble with everything except there's three exceptions. It is soluble if it's with calcium, strontium, or barium. So CaOH2 is soluble. CaCO3. Okay, CO3 is insoluble with everything, and Ca is not one of the exceptions for all anions up here. So this one doesn't matter. It doesn't have to do with CO3. So this is eggshells. This is seashells. So that's insoluble in water. And finally, SR, that should be a capital O, SrSO4. So SO4 is soluble. It's in the soluble column. It's soluble with everything except these 5. And strontium is one of those exceptions. So SrSO4 is insoluble. You put an I there. Okay, that takes care of that. I think that one's pretty easy. I think you guys all get that one. All right. Okay, next we go to the activity series. And these are generally used with single replacement reactions. It means you have a lone electrically neutral element. Over here you have a compound, an ionic compound, a metal and a non-metal, that's a molecular ion. What you want to know is this zinc and this potassium going to switch places? Are they going to switch places, yes or no? That's all you're trying to determine. And the rule is, if we'll call this the lone element, okay? It's not the ion here. The lone element. So if this lone element is above the K on the activity series, then the reaction, this switch will take place, the Z and the K that you see over here. The K comes out, becomes a lone element, and the zinc comes in and bonds with that. So the question is zinc above K? So we come over here, and K is potassium, and zinc is down here. So zinc is not above potassium. The rule is that electrons get passed down the activity series. So that means that if zinc is here, it's not going to pass electrons to K. K is a really weak guy. It's not going to take electrons away from zinc. That's the way to think of it. So this guy is not going to take electrons away from this guy. That would mean the electrons would flow up the activity series, and they don't do that. Only flow down. So the answer is no reaction. Okay, let's look at this next one right here. There's a typo here. This should be oxide, O. So that's a 2 plus, 2 minus, so that balances. So it's magnesium and nickel oxide. And the question is the nickel and the magnesium going to switch places? And let's change that to an O. Okay? So it's NiO. All right, so is magnesium above nickel on the activity series? So we come over here. We find magnesium, it's right there. We find nickel, it's down there. So yes, magnesium, the electrons will pass down the activity series to nickel. That means the nickel is going to become electrically neutral. The magnesium is going to become charged, 2 plus. So that 2 plus charge will be attracted to the oxygen. The bottom line answer is yes, that reaction will take place. The magnesium and the nickel will take places because the magnesium is above the nickel on the activity series. Again, right there and right there. Magnesium is going to pass electrons down to nickel. So yes, that reaction will take place. Okay? All right. Okay, there's one more thing that's going to be on the test, and that's a resonance structure. I didn't include that just because of space. So we'll do one of those in class, and you'll see how that works. Otherwise, review these, and you'll do well on the test. Okay? See you in class.